All right, let's go ahead and get going. So today we're going to focus on amino acids and peptides, and the sort of focus of today's class is going to be to introduce you guys to these compounds, talk about a little bit of the chemistry that's important within them. I think it's kind of neat. We'll talk a little bit about things that I think would be of interest to you guys. For example, how chemistry can take place sort of within enzymatic pockets, for example, through these processes called catalytic triads. I'm not sure your book really discusses this, but I think it's important and something that you guys should be aware of. And I think that given the fact that you guys have a certain set of skills at this point, I think that's going to be something that's going to be interesting and is going to transition to biochemistry pretty well. But you'll see a lot of the sort of factors within how nature and specifically enzymes does chemistry and can promote chemical reactions simply based upon a lot of the chemistry that you guys have seen throughout the last couple semesters of this course. Okay, so to start, let's just sort of focus on amino acids. And then we'll sort of build our way up. So we've mentioned, I think, amino acids perhaps tangentially previously in the course, but again, what a amino acid really is it's a molecule that has a structure that looks something of this sort. Again, this is the sort of charged form. You can think about the uncharged form sort of being representative as a sort of amine and a carboxylic acid, right? So amino acids literally comes from sort of structure where we have the amine, right, and we have the acid. In this case, it's a carboxylic acid. So this is generally what we're referring to. But again, in physiological settings, if you have an amino acid, again, it can depend upon the pKa that you're at. But if you think about sort of physiological pH in the sort of ballpark of somewhere around 7 or so, the molecules are going to exist mostly like this. Again, because sort of pKa of a carboxylic acid, right, we've sort of discussed in the past, it can range anywhere between probably 0 and 5 or so. Let's just say pKa, in this case, I think it's usually around 2.6, so we'll say pKa of about 3. Again, sort of in this ballpark range. And then meanwhile, you have sort of amino group. And again, amines, these can have various pKa values, but standard, we'll think of them as being somewhere around, I think 10 to 12 or so. We'll just say 12, I think that might be what the book says. But the point being, right, at physiological pH of about 7, we're sort of below the pK of this amine, right? So we're under more acidic conditions than 12, so what we're going to exist as the protonated form of the amine. And likewise, at a pK of 7, we're more basic than the pK of 3, so we're going to exist as the more charged form of this molecule. But certainly, if you're up at higher pKa's, you can imagine being a situation where you have a molecule that's only the ammonium, and perhaps this is charged. And again, if you're at sort of, if you're vice versa, and you're at sort of more basic pHs, then this is going to be the free amine, and the other part will be the carboxylate. So again, your book discusses this a little bit, but sort of there it is. I think that's the sort of important point, is that you have this sort of basic residue, and you have this acidic residue, and that sort of gives it this general name. As we'll sort of discuss, this is a little bit irrelevant as we move forward, because many of the molecules that we'll talk about will be really focused on amide bonds, and so the amine and the carboxylic acid will instead end up being an amide. Okay, in terms of the R groups, this is what we'll refer to as sort of the side chains. There's 20 natural amino acids. And the groups that can sort of be found on these vary. Again, if you want a complete list, you can go to 27.1. There's a table. I think it's called Table 27.1. That section. Okay, so you guys can go and you can sort of look at them, but we'll just sort of give you some examples of a few of them. So for example, when you have sort of side chain that looks like this, 1, 2, 3, 4. This is a molecule called lysine. So again, I've shown it in the sort of charged state, so you can imagine that physiological pH, this group would be in a sort of protic state, but often we'll refer to this as basic because of the sort of neutral form. So we're saying that it's sort of a basic residue, but in reality, what it's going to sort of exist in the sort of setting is that the ammonium. The fact that it's more basic allows it to be charged. So we can have sort of charged groups like lysine. Again, we can have groups that are negatively charged, right? So this is glutamic acid. Okay, so you can have molecules that are positively charged. You get molecules that are negatively charged at physiological pH. We also have a couple other classes, some of which we just sort of think about as strictly nonpolar. So you'll see molecules will just have sort of appendages on them. Okay, so this molecule here is leucine. So we can think about this as being sort of greasy. Sometimes you'll just have these aliphatic appendages. And sometimes you also have aromatic appendages. So an example of that would be tryptophan. This is probably a good one to mention. So Thanksgiving's coming. And everybody likes to talk about how tryptophan makes you sleepy, but they don't actually know what tryptophan is. Now you guys do. Okay, so this is tryptophan. Okay, so when somebody starts talking about tryptophan at Thanksgiving, ask them to draw it, and they won't be able to. And you can be the jerk at Thanksgiving. So anyway, so that's tryptophan. All right, so you can see there's a variety of molecules that have aromatic appendages. There's one called phenylalanine, which, as you might imagine, has a phenyl group. There's another one called histidine, which has an imidazole type group on it. Again, in terms of these greasier molecules, you have a variety. So there's ones with just a methyl group there. There's sort of an isoleucine, which is simply an isomer of leucine, as you might imagine. Again, there's other carboxylic acid-based ones, so this is glutamic acid. If you simply get rid of one of these methylene groups, that's aspartic acid. And in terms of basic residues, lysine is sort of the classically considered one, but you can also think about things like arginine, right, the pirate's favorite amino acid. Arginine. You can tell I'm already at Thanksgiving, right? But these are all sort of charged species that you could have as well, and arginine is this sort of interesting one that has this guanidino style group on it, which is interesting. So again, there's a table, you can sort of read through them, and you'll notice they can sort of be classified into these different groups, and based upon those different groups, obviously they're going to have different properties, and specifically where they're going to have these properties, and specifically where I think amino acids are important, is that you guys are starting to potentially go into biochemistry. It's important to recognize that the majority of, or one I would say of the bigger classes of biological molecules, again we have our oligonucleotides, for example, that we'll discuss next, but certainly amino acids are the building blocks, and we'll talk about them a little bit in terms of peptides and proteins and enzymes and all these things that do really important things. Okay, and so these are the sort of building blocks. Again, it's just sort of important to recognize that, you know, a lot of times you'll see something that'll have a carboxylic acid on it. Recognize that at physiological pH, right, it's actually going to be deprotonated. You'll have sort of basic residues. Again, at physiological pH, that'll actually be protonated. And as we'll sort of see, sometimes, depending upon what the other residues are within a binding pocket, sometimes there can be some different protonation states within that binding pocket. Okay? All right. Okay. So amino acids make proteins. Okay? And so the way that sort of you'll have an amino acid, right? Here's your amino acid. And what happens is, in sort of biological settings, these are clustered together through amide bonds. Okay? Where the nitrogen of one molecule, we just sort of where the carbonyl and the nitrogen will sort of form together, and we'll discuss how you can sort of do this in terms of as a synthetic chemist. But effectively what we're going to do is a condensation reaction where the sort of byproduct is water, right? We sort of mix these two together, lose water. What you're going to be left with is I'm showing the neutral state just to sort of keep things sort of easy, but we sort of, when we make that sort of amide linkage, this is what we'll sort of call a peptide bond. Okay, so this is sort of a peptide bond. Right, it's going to be that group there. Okay, and so molecules that have like a few of these are sort of what we call peptides. So once you have like maybe a small number, like say between 2 to maybe, I don't know where the cutoff between peptides and proteins emerges, but some larger number, let's say, I don't know, 30 or something like that. I don't know that there's any classification between the two, but generally when we're talking about peptides, we're talking about shorter ones. Once we get to sort of oligopeptides, this is when we start talking about proteins. And so when you have a lot of these, say for example, where now we have, say for example, n equals some very big number, for example. Now what we're starting to get to is proteins. So proteins are in general made up of huge numbers of these acting together, yes? Oh, we'll talk about it. Yeah. No, in fact, yeah, that's one way that you can make it. In physiological situations, there are processes that do this. It's actually based upon the sort of DNA template that you have, so it's the sort of transcription process. But yeah, in biological settings, the point that I was just trying to make is that in general you can conceptualize it as being these two. You're not just going to be able to take an amino acid and another amino acid, combine them, and magically spew out water and get them, right? But we'll talk about how synthetic chemists do this in a little bit more controlled way in a minute. Now, when we start talking about proteins in general, Again, when you start getting into biochemistry, you'll start talking about different sort of classes of proteins. Some of these that you guys are probably familiar with, right, is, say, for example, antibodies, right? So one big class of peptides are antibodies, right? So antibodies are huge proteins that look something like an upside down, sort of an upside down Y, right, where we have two portions to them. And again, this is just sort of so you guys know how antibodies work. There's a sort of an FC region and a Fab region. And this is the part that will actually recognize bad things, right? So the way antibodies work is that they'll have one portion of the antibody that will actually literally sort of, well, not covalently, but just through sort of non-covalent interactions generally, just sort of bind to, say, for example, sugars, right? Like we talked about the other day, maybe some foreign sugar. And then the FC region is the sort of flag region, if you will. This is the part that's actually going to have a specific purpose. So there's different classes of antibodies. They generally differ in a couple of different ways, but many of them have a similar FC region because they all sort of have that same effect. So maybe they're flagging down white blood cells, maybe they're flagging down an early complement protein. But again, this sort of whole overall shape is made up of a whole bunch of these different peptide bonds in a specific way that leads them to this sort of ability. Another group of proteins, right, are enzymes. Right? Enzymes are big clusters of amino acids together in proteins that serve a specific catalytic function generally, serve function as catalysts. So again, all the sort of physiological processes generally that take place in your body that are sort of chemistry at their heart are often done by enzymes. And just to kind of give you an example of how enzymes might do this, usually what will happen is there will be some big binding pocket, right? So there's lots of peptides, right? So there's like lots of protein out here, right? The protein is just lots and lots of these peptides. And then generally what happens is that there's a pocket that these things can bind into, generally specific for a specific substrate. This is why enzymes can be really specific. And then generally built within there, there's a few residues that are sort of pointing in specific directions, and they will give you certain types of chemistry. So say, for example, if you have a molecule like a cysteine, to say. Okay, and then you have cysteine is with the sulfur. Okay, but you could have, let's say, okay, so sometimes what will happen is you'll have this sort of system where you have a catalytic triad, where what you'll have is, say for example, you'll have like a Lewis basic site here, right? You'll have this sort of nucleophile here, and you'll have this sort of Lewis, you'll have this sort of this basic site here. And what will often happen is through a sort of a network of molecules, you can do things like deprotonate an alcohol, right? So an alcohol, the pKa of an alcohol is only like 15, right? So physiological pH in alcohol isn't per se going to exist as an alkoxide. But oftentimes through networks, such as what I've sort of shown here, what that creates is a system where you can begin to sort of activate carbonyls like this. So sometimes there'll be some proton things that will sort of activate this carbonyl. This would be your sort of a substrate, for example. So let's pretend that this is an amidase, right? So if we're going to sort of cleave this amide, you have this sort of network. What's going to happen is this is going to come up, and you'll actually put the carbonyl onto this nucleophile. So this is fairly common. So you'll have something like serine. The serine will start by actually adding into the amide. And then generally what will happen is then subsequent step will come where, say, for example, water comes and cleaves it. So common types of catalytic processes that enzymes will often carry out are things like hydrolysis of peptide bonds, right? That would be a peptidase, for example. Similar things with phosphoroesters, for example, those would be called phospholipases, like we saw earlier. Yeah, Margo. A synthase? Anytime you hear of an ACE, yeah, right. Well, this would be like this would be an amidase, I guess, would be the case of it, because you're taking an amide and you're cleaving the amide, so it would be an amidase. A synthase, I guess, would sort of be more general, anything that might perform synthesis. I'm not really sure, but this would be specifically like an amidase. But again, the sort of point is that through sort of a network of systems that are sort of created by amino acids building up, creating these sort of secondary structures, right? Because it's trying to build up kind of like peptides, you'll sort of build up these secondary structures. Within enzymes, what you begin to get is these sort of networks of residues, which can begin to sort of catalyze reactions. So if you want a sort of an interesting read, look up sort of catalytic triads, for example, and you'll sort of see how different networks of different groups can sort of come together to carry out specific catalytic processes. And again, it's sort of two things that's kind of interesting. On the one hand, the enzyme will create a pocket that might be selective for a given substrate, right? So if you want something that's only going to, say, for example, hydrolyze tryptophan amides, right? There might be some binding site for that tryptophan residue within there, which might make it selective towards compounds where that's the bond that you want to cleave. And so there's sort of one aspect that's a sort of binding pocket, and there's the other aspect that's sort of chemistry that's actually not too different from what perhaps you guys have seen in the past. Okay. Now, as synthetic chemists, this is sort of what you'll get into more in biochemistry. As synthetic chemists, the sort of question really comes up, how might we actually synthesize peptides? And so what we'll do is today we'll discuss a little bit of the synthesis of peptides, some of the things that we do. There's a lot of reactive elements on these compounds, so we'll talk about sort of strategies that go into making amino acids. And then again, what we'll talk about next week is how you can translate sort of from synthesis of maybe smaller peptides, perhaps synthesis of bigger proteins and so forth. And that'll be the stuff that I mentioned will be in your, I put on some material sets like chemical ligation and so forth. And so here's a couple examples of proteins. Certainly there's tons in collagen, for example, something you guys have heard of that's made of this. And others, sort of everywhere. Okay, so as was sort of brought up, right, we're not simply going to be able to take an amino acid and simply have it react together and form a sort of an amide bond. Again, in physiological settings, we have these types of enzymatic processes which effectively allow for this to happen in a selective and specific way. Now, if we're going to be doing this in a chemical lab, we're going to run into lots of problems. We're not going to be able to simply take this and this react together, because certainly this compound could react with itself, right? Because you have an amino and a carboxylic acid here. On this side, you have an amine and a carboxylic acid over here. And so a lot of peptide chemistry and amide bond-forming chemistry within peptides has a lot to do with protecting groups. And so protecting groups become a fundamental aspect behind this sort of chemistry. And so I thought I would start by just sort of talking about sort of amine protecting groups. Because again, if you just start thinking about it, if you want to do this chemistry, and you had this amine protected, well now this is no longer going to be able to react with itself. Right? And we'll get to the carboxylic acids next, but let's just start first with the amine protecting groups. And so within peptide chemistry, there's a few main ways that we can do this, but they often involve sort of carbamates. Okay, so what the carbamates effectively break down to is that you have CO2, you have some R group there, and so what we'll see is we'll put them on, and then generally what happens is when we take them off, you will get your free amine, you will get carbon dioxide, and then you will get some remnants of this R group. And we'll discuss that a little bit. And so a lot of work has gone into making protecting groups that are what we call sort of orthogonal, right? So what's sort of important within protecting group chemistry is okay? And what I mean by this is protecting groups that you can sort of put on under conditions that aren't going to give you problems perhaps later on, but more importantly, since you can generally put those in your fragments, what's more important is that you can take them off specifically. So a lot of work goes into protecting groups that, specifically orthogonal protecting groups. So, okay, I have this protecting group here, I want to take this one off selectively, and I don't want this other one touched. And so a lot of work has sort of gone into this. And so in terms of acid-sensitive amino protecting groups, perhaps the most common is called Bach. Okay, and so if you have sort of amine, what you do is you can take it and you can treat it with this compound, which is called Bach anhydride. So again, you have, this is sort of anhydride, and as we'll discuss, this is sort of considered the Bach, sometimes called T-Bach because it's sort of T-butyl group. What happens in this reaction is that your amine is going to sort of attack this group. Okay, it's going to sort of fall off, and what you'll get as byproducts are CO2, as well as, once there's a subsequent protonation, P-butanol. This is another fairly important thing about protecting groups sometimes, is that the byproducts are volatile. Right? CO2 is certainly a gas. P-butanol is not the most volatile thing, but certainly you can get a rotovap, for example, to I think the boiling point's somewhere around like 80 or so, or 90, but certainly it's something that you can get off under vacuum in the presence of these other things. And you end up with is this group here. And so this is considered the Bach group. And again, what it sort of stands for, sometimes you see it as TBOC. And so what it sort of stands for is terp-butyl, like oxycarbamate or something like that. But the important point is that B is sort of like the T-butyl component of it. Now you can carry this through a lot of different steps. One of the nice things about T-butyl groups, this protecting group specifically for carbonyls, is that this group is really bulky, right? And so if you had something that was a good nucleophile, say for example, like another amine around, that amine is effectively going to be protected from adding into here because of the bulky T-butyl group. That's the first thing. The other thing, this is a carbamate, right? And so it's a little less nucleophilic inherently based upon the lone pairs that are donating back into here. So it's not quite an ester, it's not quite an amide. Again, it sort of has these two groups donating in, and so it's less reactive inherently than a standard amide or a standard ester. So it's not going to be as likely to hydrolyze. And so it's really those two competing factors that make it unlikely to react with other nucleophiles. However, you can take it off fairly readily by taking it to slightly strongly acidic conditions. And what you do is you're going to take this group, and so if you want to deprotect it, what you're going to treat it to is an acid called TFA. TFA is trifluoroacetic acid. We've talked about trifluoroacetic acid in the past. There's two important things about it. The first is that because of those three fluoride groups, it's a little bit stronger of an acid than, say, acetic acid. So the pKa of acetic acid is somewhere around 4. The pKa of TFA is somewhere around 0. So by having those three fluorides there sort of stabilizing that inductive withdrawing, it's a little bit easier, it's a little bit stronger of an acid. The other thing about TFA is there's this impact of having fluorides. This is fairly common in fluoride-containing organic molecules, that the boiling point is actually fairly lower. Even though it's heavier than acetic acid, TFA is actually fairly volatile. It's got, while the boiling point of acetic acid is, I think, like 120 or something like that, fairly high, the boiling point of TFA is much lower, like 70 or 80, somewhere in that ballpark. So again, you can sort of rotovap it off fairly readily. We can get rid of it. And so we can effectively use TFA oftentimes as the solvent. It will often serve as a solvent. Generally, though, people use it as a mixture with dichloromethane. But what happens is you'll actually deprotonate the acid, or I should say protonate the carbonyl. And when you do this, what you end up having is that, right, that positive charge in that position. And what can happen, right, in this situation is the terp-butyl group, right, can sort of leave behind a terp-butyl cation. Okay? So what will happen is this can just fall off, leaving behind a sort of stabilized T-butyl cation. Sometimes there's sort of, for example, water in there that can trap that and regenerate and sort of generate terp-butyl alcohol. Other times people add things that are slight reductants that will effectively generate do elimination stuff, but generally that's not an issue. It's a fairly stabilized cation, at least throughout the process until it gets quenched. And then once you're here, this falls apart very readily through a mechanism which you could perhaps draw on a couple different stages, right? You could perhaps protonate this first. Right, we sort of draw it in that different proton form. What you can see is that very quickly you will expunge carbon dioxide, right? And get to sort of mean, okay? So this is perhaps one of the most widely used protecting groups. It's called a Fox protecting group. It's used very widely in peptide chemistry. And so, and again, it's going to be stable to nucleophiles, but you can take it off under a sort of fairly mild acid PFA. It's kind of funny, I use that term fairly mild with a collaborator of mine who's a biologist, and they don't tend to think of TFA as being all that mild. But at least we think of it as being a fairly mild acid, to sort of work with. Okay, so that's if you want something that's going to come off under acidic conditions. There's another protecting group that you can put on as well. That is what we call a CDZ group. Okay, and again, if you sort of just think about the mechanism here, right? It's just like an acid chloride. Why this one is chloride, the other one an anhydride, I'm not sure. There might be versions of these that are anhydrides as well, but this is generally the way that I see this done. And so this group here now is called a CDZ group. So it's analogous to a Bach, but you can see instead of the sort of T-butyl group over there, what we're now going to have is a benzyl group. Okay? And again, the mechanism should be straightforward. This molecule now is going to be a little bit more stable to acid. So if you treat this molecule with TFA, it's not going to fall apart. Again, because you don't have that stabilized, that would be a sort of a primary carbocation, even though it would be stabilized by the aryl group, you wouldn't necessarily want to generate a primary carbocation. However, what you can do with this reaction is you can do a sort of hydrogenation. And so generally if you take it with hydrogen gas and specific metals, I don't know which specific metals, usually it's like palladium on carbon, I think. But I'm sure there's different ways that you could do that. What happens is you can actually cleave this molecule as well and go back to the amine. And the reason why this sort of reduction works at this step is that you can, in essence, reduce. I tried finding a specific mechanism for this. I've never really found something that's exactly what I've been looking for. You know, what you find is that toluene is generally sort of made. So I suspect that the hydrogenation has something to do with that there, again, because the byproduct is generally, in this case, CO2 and toluene, which is, again, volatile. But the mechanism that I've often sort of used to at least rationalize this, whether or not it's correct or not, generally has to do with hydrogenating a specific bond in that alkene, right? So you get to something like this, right? If you can sort of hydrogenate one of those double bonds, that is the way that I've always rationalized it. What can happen at this point is that you can effectively do a I'll just push them all the way over, just for the sake of time. So it's going to be more similar to over there, but the point is that you'll get the amine. And then what's left over, right, is a molecule like this. Right, and this is simply a sort of a proton. Again, obviously that's not going to happen that way. It might be two molecules, but it's effectively a proton transfer to sort of aromatize the molecule. So again, obviously this specific mechanism is going to happen. It might be another molecule comes in and does that, because obviously this molecule isn't going to reach on that side, but it could be bimolecular or something, but it's effectively and formally a proton transfer from one of these two protons over to this group to effectively generate toluene. Again, I tried to see if I could find a specific mechanism for this. It could just be hydrogenation of that bond as well, but this is sort of how I've always reasoned it. It's sort of the hydrogenation of a specific alkene, yeah. Mm-hmm. Here? So if hydrogenate this further, I'm not. Oh no. That would be oxidation. You're gonna put two protons in, not take two protons out. We can hash out your idea maybe on the board afterwards or something. But yeah, no, I mean you got to add two protons in. And again, I'm not necessarily sure if this is the mechanism I've seen, and the reason why I've never found a mechanism that I've been necessarily comfortable with is perhaps it's not known. It may just be that this bond you can hydrogenate directly, for example. And again, I've seen examples where other aromatic groups remain untouched, right? Which makes me think that this probably isn't what's happening, but at least it's something that you can rationalize given what you guys know as a mechanism. But again, the point here is that now this is a reductive cleavage. Okay, and these are both discussed in your book. The one that I don't think is discussed in your book is the sort of base sensitive one. Okay, so here's acid, here's hydrogenative. I'll show you the base one as well that's generally used. So again, just so you know, this group here is called a CBZ. And again, I think it's like carbamate benzyl or something like that. I forget what the specific name, what it's sort of for. Okay, the last one we'll sort of discuss is the base sensitive amino acid protecting groups. And in this case, the sort of go-to one is what's known as an FMOC protecting group. We'll discuss these a little bit more next class. But the FMOC protecting group is a little bit more complicated than some of the others. It's not as easy to sort of get rid of the byproducts as the others. And so as we'll see, this is generally used with solid phase synthesis, which we'll discuss next class. And again, if you sort of go through that mechanism again, right? Look at fluoride, and we'll get to this FMOC protected group. Okay, so this is FMOC. And, oops. Sorry. And the sort of name for this stands for fluorenyl methylene. So this is a fluorenyl group. This is a methylene, so fluorenyl, methylene, and then sort of whatever oxycarbamate or whatever the sort of ox stands for that you see in all of these. So this one's going to be stable to acid. I'm not sure if this is going to be stable to hydrogenation or not, but again, it's not a benzyl. The benzyl group's not directly attached, right? So it probably wouldn't be sensitive to a benzyl group either. It's not going to come off necessarily under benzylations. But what it will come off under fairly readily is basic conditions. And specifically the base that's often used is piperidine, which is an amine base. And what I thought I would do is ask you guys what you think the mechanism for this might be, and why this group, so take a look at this molecule, draw it out. What might it be about this molecule that might make it actually basic, sensitive to base? And think about pKa, think about what type of mechanism might happen here. If we're going to have a base and we're going to eliminate carbon dioxide, what type of mechanism, analogous to what you've seen in the past, what you imagine might happen here? Yeah? One where the ketones, so you want to directly add here? Yeah. Okay. But we've seen that that doesn't happen in the literature. It's a base-mediated process. And so there's going to be, and when I'm saying base, I don't mean Lewis base, I mean Bronson base. So there's going to be a proton on this molecule that's going to be more acidic than what we've seen in the past, from other instances. So that proton right here, what's special about that proton if we were to deprotonate it? Yeah, there's a ton of resonance here. It's effectively, in a way, got these two benzyl groups that could sort of resonate throughout it. And so if you were to imagine a negative charge there, now you could effectively resonate that negative charge throughout the entire system. And so what happens here now is that the base is going to pluck off that proton, and then once you pluck that off, you can simply do the same elimination that we've seen previously. So now only under basic conditions. So you'll generate CO2, you'll effectively generate an alkene there that might be reacted in some other ways further down the line. But what you get here is that molecule, again, CO2, in this case, something that looks like this. And again, I'm not sure if this now reacts with other things, and maybe the byproduct is something a little bit different than that, but you can sort of see that elimination process. Okay? And so FMOC is generally the one that people mostly think about when they're thinking about doing, when they want to remove it in the presence of a base. Yeah?
Is it in any way to get with an indicator during that system of the color change that happens that would tell you the off versus on?
I don't think so, but I would be shocked if people haven't made derivatives that would do that. Again, I think the point that's being brought up here is that you have a very conjugated pi system, and by perturbing that pi system, you may actually end up seeing color changes. It's an interesting idea. I bet you people have thought of that and have used that, and if not, they should have, because that's a good idea. So you can sort of know when your reaction's done just by looking at the color and seeing when the color's done or something like that. Yeah, that would be cool. Maybe, I don't know. Okay, so these are the general sort of groups that we use, probably the three most widely known. There certainly are others that might sort of fall in that category again, but at least now you've seen three different examples of compounds that are cleavable under acidic, basic, and both hydrogenated conditions. And again, you guys could probably design, for example, a protecting group that would have the silyl group on there, and take that off under fluorous conditions, right? That wouldn't be too much of a stretch. But yeah, so here it is. All right, so once you have your protecting groups, now you can start to begin to think about putting these bonds together. And so if now we're in a situation where we had now we protect, we haven't gotten to the carboxylic acid groups. There's also a lot of times you can protect carboxylic acid groups as well. They aren't going to fall off necessarily as well as what we've seen in the past. But again, you can imagine a benzyl protected carboxylic acids, these certainly you can take off under hydrogenated conditions as well. And there's others that you can do as well, but what I just thought I would mention that really quickly, because now we'll sort of use this to sort of think about our strategy for putting together amino acids. Okay, so what you'll do if you want to start to make peptide bonds is that you're going to take your amino group that's going to be protected with one orthogonal protecting group. So now we've got something that's stable to, say, acid and base, but can be taken off under hydrogenated conditions. And what we'll do on the other side is we'll have a carboxylic acid. On this side, maybe we'll have a Bach group. On this side, so I'll just sort of abbreviate that Bach. And so this is going to be, so this will be acid, okay, H2, metal, reactive. Right? So it's safe under acidic, it reacts under these conditions, and on this side, this is sort of acid reaction that's going to take place, and under H2 and metal reduction conditions, we're safe. This is going to be stable under reductive environments, but we can cleave it under acid, and this is going to be vice versa. So this is what we're talking about when we're saying orthogonal. One will react under one set of conditions, the other will react under the other, and there's not going to be any cross reactivity, or it's going to be very limited. Okay? But now what we need to do is we need to sort of connect these two and make this amide bond forming process. And now there's many ways that you can imagine doing this, right? Someone brought up, for example, can you turn it into the acid chloride, for example? Certainly that's one thing you can imagine, right? You take the carboxylic acid, you turn it to the acid chloride, and that would be fine. The problem, though, with acid chloride, well, certainly in this case, the problem with acid chloride would be the Bach would fall off, right? Because we'd be under two acidic conditions. The other problem with things like thionyl chloride and oxyl chloride in peptides is that the peptides can begin to react with these as well. So to make the amide bonds, we need something that's going to be a little bit more neutral, if you will. And the standard way that people go about doing this chemistry is using a molecule known as ECC, or different carbodiamides. Okay, so this stands for dicyclohexyl carbodiamide. Okay, and what's going to happen when we treat the two with these as well as base is we're going to make our peptide bond very cleanly. It's a very good reaction. Although there are some problems with it, and we can discuss. So, for example, Tristan Lambert, who's somebody down the road at Columbia, one of his projects he's working on is coming up with alternatives to this reaction because it's so widely used, and yet, as he sort of classifies it, it's sort of something that's considered a solved problem because people have used this so widely, but there are some fundamental issues that could still be addressed. Okay, and so at least from a strategy standpoint, right, you can now start to see what would happen, right? You can make, and we'll talk about the mechanisms of DCC in a second, but I just want to sort of discuss this strategy, right? We're going to take these two, we're going to put them together. Now we've got these two groups here, right? So depending upon which side we want to build off from, we can either hydrogenate this and build off this way with more groups that look like this, right? Because this sort of N terminal will be protected in one way. Or we could do it the other way around. We could go ahead and take the Bach group, take off the Bach group with this being here and build off that way. So there's orthogonal nature that depending upon what you want to work with, you can build in one way or you can build in the other. And it turns out that sort of, as we'll often say, sort of N to C, whether you're starting from the nitrogen going to the carbon, or C to N if you're going in the reverse direction, there can be certain advantages to going one way and there can be certain advantages going the other way. But at the end of the day, it really doesn't matter as long as you can make the compound. And at least there's nothing that can hold you back in principle from building up one way or building up from the other way. And so again, this sort of orthogonal nature means that you can protect one in the presence of the other and continue to do this process until you make lots and lots of amide bonds. All right, so how does DCC work, and why does it work? Okay, so this is probably going to be one of the little bit longer mechanisms that we've seen in a little while. Actually, I don't think it's too long, but we haven't really seen the mechanism in a while, so I guess by default it's going to be a little bit longer. But what generally happens is when you've got a carboxylic acid, right, and you've got DCC around, we can draw this in a few different ways. I'm going to just sort of show it in a neutral state, and we'll just do proton transfer just so we can sort of track what's going on here. So we'll sort of ignore the base to a certain extent for now. And we'll use the carbodiamide as this sort of internal base. Okay? What's going to happen in the first step is we're effectively going to get to a more nucleophilic carboxylate, right, and a more electrophilic carbodiamide by effectively transferring that proton from the carboxylate over to the carbodiamide. Okay. Now at this step, we're going to sort of make a bond, and effectively what we're going to do is we're going to turn this carboxylate into a better leaving group. Okay, so what's going to happen is this carboxylate is going to attack that carbon and effectively push the electrons onto the positive charge here to neutralize that charge on that side. Okay. Now what we have is something that's a little bit of a better sort of leaving group. Okay, we've got a group on here that's effectively going to break down and form what we'll see is a sort of a urea, but this might now begin to sort of look like a molecule that we've seen in the past that's a pretty good electrophile. Anybody want to take a stab at what the heck I'm talking about? What does this might start looking like to you, especially the way that I've drawn it? What type of reactive carbonyl that we've seen? Yeah, right? See how this kind of looks like an anhydride, right? You've got a sort of a carbon-nitrogen double bond over here, carbon-oxygen double bond here with the oxygen in the center. So it's beginning to look a lot like an anhydride, which, as we know, is a pretty good electrophile. Okay? And so what will happen here is now your amine can add in. Okay? And what I'll do is I'll just do a proton exchange as well, just to show the sort of intermediate. And this is one of those mechanisms that I think we can draw a couple different mechanisms for. But I'll show one this way just to sort of save board space, and since I don't really think there's anything wrong with drawing this way. In fact, this might actually be how it works. Okay, so once I added in, I did a proton transfer. So this would have been NH2+, this would have been O-. So I simply did a proton transfer from one side to the other to get here. Okay? And what can happen here now is, again, that sort of magical number 6, right? We can effectively protonate this nitrogen in a way, make this nitrogen-hydrogen bond, through the process now break down this carbonyl to generate the amide, and again, then sort of finish with those last couple bonds, go over to that carbonyl. This is probably what happens. I mean, this is certainly the product, and I guess I mean that's probably the mechanism. In the process, now you get your gamma bond. Okay? All right, so that's the basic mechanism for DCC coupling. Yeah.
Why can't we use this kind of, why do we use
Like from here, I put a negative charge there. Why couldn't you just kick it down and leave? Yeah, that would probably be fine as well. But there still needs to be a series of proton transfers from here to here. Sure, yeah, that's fine. That's fine as well. This is just kind of how I drew it for border space in the way that I was sort of thinking that it would take place. Okay, so this would get to your amide bond. And again, as I'm sort of looking at this mechanism, I'm pretty sure that you usually use a base in this reaction. But now I'm not quite sure why that would be the case. It might be to, when I'm thinking about it, you may use an equivalent because oftentimes you have the ammonium, the NH3+, and so you may use an equivalent of base simply to make the free amine, but I'm not really sure. But it's clearly, you can see we got through the mechanism just handy-dandy without a base in there. Now, the one issue, and this will come up next week a little bit more in terms of sort of problems that you can sometimes get with these molecules, is that the byproduct can often be a little bit of a pain in the neck to work with. Does anybody know what this molecule is sort of called? I think I heard somebody say it. Urea, yeah, so that's urea. So this is like one of the components of urine, exactly, right? So, yeah, so, right, so this is, right, so this is urea. And so that's effectively what that is. It's a dicyclohexylurea. And the problem with dicyclohexylurea, and this is one of the reasons why I think this is one of the things that Tristan in particular will bring up on occasion in terms of the problem with this chemistry, is that when you're doing standard amide bond coupling reactions, you always get this as a sort of side product. And some people will talk about this sort of idea of atom economy, as that you're sort of wasting all of this component of the molecule to simply make the molecule, at least in terms of towards an ideal synthesis, if you will. But the other practical issue is that if you don't worry about costs and this sort of idea of atom economy, what you do have is a molecule that can often be a real pain in the neck to get rid of. So our general method of purifying compounds is chromatography. Right? So you guys have learned chromatography in Organic 1. Not sure you've used it all in Organic 2, maybe you have. But urea just hangs to that column, it just bleeds through. So it doesn't necessarily come off very cleanly. And so oftentimes what will happen is you'll be running your column and you'll end up running 4 or 5 columns just to get rid of this byproduct. And so one of the things that people have come up with is alternative compounds that are, for example, more water soluble. So there's examples of this that there's a compound called EDC, for example, that has an ammonium side chain off the side that allows you to, for example, wash it away with water. So just recognize that there's that urea, and occasionally you'll see sometimes you'll see DCC as kind of the standard, but occasionally you'll see other classes of these that people will use, and there's various reasons for that. But DCC, which is, again, this is DCC. This is kind of the go-to one. Yeah, so the other molecules, I don't want to screw up EDC in the drawing of it, but yeah, so it's sort of like, I forget exactly what EDC, the structure of EDC is. But yeah, it has like this general structure, and so the product has urea, but what it will change is, like, for example, that R group will have an appendage on it that now you can protonate. So I think there's like an amine side chain handing off of it, and thus you can take it up under slightly acidic conditions, and it will go into the aqueous layer, and you can extract your stuff out of the other layer. So those are some of the tricks that people will occasionally do. So yeah, so that's where it would differ. It would be the same in here, so the chemistry would all be the same. All right, so we'll get more into some of that next class. We'll talk about sort of solid phase synthesis and solid supported synthesis and the like with that. With the remaining class, what we're going to sort of focus on is a couple things that involve sort of mechanisms. So we'll talk very briefly about Edmond degradation, which is a sort of classical way that people go about and then subsequently MS analysis. So I might not have time, maybe I might have to talk the beginning of next class on MS analysis, which will actually be, you'll have to go back and read an earlier chapter, but I think it's important to sort of know how people determine the structures of these compounds. And so Edmond degradation is often in here as a historical perspective, but generally nowadays people don't ever use Edmond degradation as a way to sort of know what a peptide structure is. So if you have, say for example, a peptide, and let's say for example it's but whatever, it doesn't really matter. But let's say that we had so here's a tripeptide that I'm going to sort of show you guys. Okay, so here's a tripeptide. Basically, it's composed of 3 amino acids. And if you want to sort of figure out what the general structure of this molecule might be, it may be a little bit difficult, right? Because NMR, sort of to know what the sequence is, to be able to sort of look through multiple bonds and understand, you know, there may be ways to go about it, but it might not be, or it isn't really the sort of easiest thing to sort of do. You can get a mass spec of this molecule, right, and what that might help tell you right away is what the overall mass is, and from that overall mass you might be able to deduce what the different residues might be. You can certainly take an NMR and maybe you'll see a phenyl group and a benzyl group that might tell you that it's a phenylalanine. You might see the methyl group that might tell you that there's a methyl group in there. And you might see the methylene that might tell you that there's that methylene there from alanine. But what you might not know is what is the sort of sequence. Where is everything within that sequence? And the classic way that people used to do this was something called a sort of an Edmond degradation. And what an Edmond degradation is it effectively allows you to chop up the peptide sort of one amino acid group at a time. So it starts from the N-terminus, and what we'll do is we'll react with that N-terminus to generate a new, we'll go from a tripeptide to a dipeptide, right? We'll know what the components of the of the leftover thing will be. That will tell us what the first residue was, and then you can do it with the second residue as well. So you can go on and on and on through that sort of sequence. Okay? And so the key reagent in an Edmond degradation is cyanogen bromide. Okay? Okay. So what happens in an Edmond degradation is you take cyanogen bromide, you sort of react these two together, and the product that you're going to get in this case okay, so you're going to effectively cleave the amino acid at that position, okay, and then, oh sorry, wrong compound. Jump that, not cyanogen bromide. That's a different reaction. It's phenyl isothiocyanate. Okay, so what's going to happen is you're going to effectively cleave the carboxylic acid group, and what you're going to be left with is what's called a phenylthidantoin. And the structure of the hydantoin is okay? And in this case, what our R group is going to be, right, is it's going to be the component here, right? So if this was, in this case, R equals H, okay? So what happens is we'd get a new phenylphydantoin. We'd be able to isolate it. And what we would see is that there's this methylene group here, right? And what that's going to tell us is that the first amino acid in this process is going to be, in this case, alanine, okay? And the other thing that we'll have is this dipeptide over here, which should be the remaining groups which you can use to certainly confirm that everything's going all right. Okay, so mechanistically, how does this work? So when you do an Edmond degradation, what happens is, we'll just focus on this will be the rest of the peptide. What's going to happen is the first step, as you might imagine, is going to be the amine. It's going to attack that carbon, okay? And this sort of process, you can push the electrons up into the sulfur, or you can push the electrons onto the sort of nitrogen. Okay, so it might go up into the sulfur and then back down to the nitrogen, but pushing into this nitrogen, given the fact we only have like 2 minutes left, is what we'll start with. Okay? And then what's going to happen is now we're going to effectively cleave that amide bond intramolecularly. Okay? So this is going to add in here. And we're going to sort of cleave that bond. Okay? The overall process, right, will lead to the rest of the peptide. Right? And then our hydantoin. Where does the phenyl group? Which in this case, that R would be a proton, okay? So you would continuously do this, so you would do this once, right? Now you take, in this case, I just did a simple tripeptide. You'd break down to a dipeptide. You would know what the first amino acid residue would be. Then you do it again. You'd get a second one, and you sort of generally break that down. So I would say certainly from a problem-solving standpoint, if you find questions that deal with Edmond degradation, they tend to be pretty easy ones to write problems with. So I would know how to sort of know the overall degradation, the Edmond degradation product. And then what I will do is next week's class, I'll introduce you guys to solid-supported synthesis and native chemical ligation. But before that, what I'll tell you about is the sort of current method that people use to determine larger peptides and protein sequences, because I think that's valuable for you guys to know. Okay, so with that, again, as a reminder, my office hours today, there's a faculty candidate again today, and they have their talk is at 11:15, and I have to go to it. So I'll be back in my office at 12:30, and I'll be there till 2 o'clock-ish. So, hi.
I emailed you over the weekend.
Yes.
For tomorrow.
Okay. What time?
What time are you thinking?
Mornings are generally better. I leave around 2:30 or so. So I would try to come by early, 8, 9. When's your class?
I'm free after 10:45.
Okay.
So I can start my head. Okay.
Do you have to leave right away?